Right, welcome back. Statistics. This is going to be a video dealing with section 12-2. There will be at least two videos on this section. There are two different tests that we learned in section 12-2. I have the name of the first test, though, written up here, the chi-square test for homogeneity. Okay, the other test is called the chi-square test for independence. You'll see that they look very much the same. They're run very much in the same manner, but there's a subtle difference. Anyway, we're in this video. I promise you, all we're going to do is we're going to talk about just the one test. What this test is designed to determine is whether two or more populations are homogeneous with respect to some characteristic. Okay, I think that the best way to proceed is just to jump right in and do an example. By the way, I apologize for this hair. My regular hair was getting quite long and kind of shaggy and such. And, of course, you can't get a haircut these days. So my wife, who is an excellent cook and an all-around wonderful person, she's in the process of cutting my hair. She's not a hairdresser, and right now it has some issues. She's gonna work on it some more this evening. So maybe by tomorrow, I'll be presentable. Anyway, let's proceed. What we want to do here is, you are all quite young, and whereas I'm kind of old and such, and I don't know if we like the same television shows. I don't know if we even know about the same television shows. And so what the study I'm going to describe here is going to be about is, are television viewing preferences the same for young people as they are for older people? Okay, and we'll draw a line in the sand, and we'll call old people 40 plus. Okay, I mean that's not like old like an old man necessarily, but you got to draw the line somewhere. And then young people, into which the category into which all of you fall is going to be under 40. Okay, now it turns out I have some data about this. And what I'll probably do is just kind of erase all this so I can make a table. Okay. The chi-square test for homogeneity, as well as the test for independence, both involve what's called a two-way table. Again, I'll explain what that means here. A two-way table is going to be a rectangle or a square or something like that. And what you do is you're going to make cells within this table. Remember with the chi-square goodness of fit test, you had like a row of cells. It was just a 1x3 or a 1x4 row of cells. With a two-way table, you're going to have at least two categories along this side and at least two categories along this side. But you can have as many as you want. Now, what I'm going to do is I'm going to divide this into young and old.
Oh, no.
Okay. And then there are three television shows that I think that probably everybody, young and old, have heard of. There's probably more than that. But I was going to choose The Office, Parks and Rec, and The Simpsons. Okay. And then what we're going to do is we are going to, and this is important, what I'm saying right here is important. What we're going to do to investigate whether the television viewing preferences of young people are the same as television viewing preferences for old people. And here it comes. We are going to randomly select a sample from the population of young people. And then, as a totally separate process, we're going to randomly select sample from the population of old people. Okay, it's two separate samples for the chi-square test for homogeneity. Okay, well, it turns out I selected or I have data from a sample of young people, and let's see, it shook out like this. Out of the 400 young people that we asked, 250, oh, that marker doesn't work. I'll stick with black. 250 said that their favorite from among these three shows is The Office. 100 said Parks and Rec, and then 50 said that The Simpsons was their favorite show. Now, I also have data from a random sample of people 40 and over, and for them, it broke down like this: 220, 130, and 50. Actually, let's change that to a 120. Sorry. And 4. That would be 60, wouldn't it? Okay. Now, take a minute, maybe on your piece of paper, and just jot that table down. Okay. We had a random sample of 400 young people, a separate random sample of 400 old people, and this is the number of people in each sample that said that this was their favorite show, or this, or this. Okay. The reason I'm telling you to jot that down is because we're going to do some stuff with that table. Okay. But before we do stuff with the table, we are going to begin where we almost always begin, with a hypothesis test, by writing a set of hypothesis statements. Okay. In this case, the null hypothesis is that the category proportions are the same across all categories. There's a couple different ways to say that. I'm going to scroll in my slideshow here to exactly how the textbook phrases it. Proportions in each TV category. My marker's starting to wear out a little bit. I'm gonna try to get it. Teddy, will you give me a different marker like out of that box or something?
Oh, where?
Well, there's some boxes right over there.
Oh,
Is there a box of blues? Thanks, I appreciate it, boy. Okay. The proportion in each television viewing category are the same for young and old people. Okay. Can you read that blue okay on the screen, boy?
Yeah, sorta.
Okay. Sorry if that's a little blurry. I'll read this. It says the null hypothesis is that the proportions of TV viewing preferences, okay, or TV category, the proportion of people who like The Office, the proportion of people who like Parks and Rec the best, etc., are the same for young people as they are for old people. Now, you can look in the table and you can see that it's not exactly true for this sample of people, but is that due to just sampling variability? Did we just get kind of an unusual sample, or is the null hypothesis not true? Okay, so the null hypothesis is that we expect the same proportion of people to prefer The Office among the young people as we would among the older people, and Parks and Rec and The Simpsons. Okay, now the alternative hypothesis is kind of like it was for the chi-square goodness of fit test. Okay, I'm going to erase the null hypothesis now and write the alternative hypothesis. Okay, so H sub A is simply that H naught is not true. Okay, that is the alternative hypothesis. The proportion of people who prefer each TV show is not the same among young people as it is among old people. Okay, now we are going to start to work with this table. Okay, the very first thing we need to do is we need to add up the row totals and the column totals. Okay, so you can do that along with me here. I know that the row totals are 400 for each one of these, because those were the sample sizes, but I just add across to get 400. And then for the column totals, I'll add down. That's going to be 470. That's going to be 220, and that'll be 110. And then finally, after I've done the row totals and the column totals, I'm going to write the grand total right here. The grand total goes right here, which means you can either total up the row totals or total up the column totals. But either way, there were 800 people total involved in this study, 400 young people and 400 old people. The sample size does not have to be the same for young and old people. That's not necessary or anything. They just happen to be in the set of data that I had. Okay, now, in each cell here, those are the observed cell counts. And if you did section 12-1, you remember that those are just the counts that we observed from our samples. And into each one of these cells, now we're going to put the expected cell counts. Okay, now let me tell you how to get the expected cell counts for a chi-squared test for homogeneity, and it's going to be the same for the test for independence. Okay, expected cell counts. Okay, you take the row total. I'm not going to have enough room to write it there, so I'm going to write this underneath it. Okay, expected cell counts, you take the row total times the column total. Teddy, can we read this? And then I divide that product by the grand total. Okay, now, so I have to do that for each cell. So I'm going to do a demonstration of how to do it for just this, maybe this top leftmost cell here, how to get the expected cell count for that cell. And I'm going to use this formula right down here, row total times column total divided by grand total. I'm going to erase this because I'm going to need the room to do the arithmetic here. So for this top left cell here, the row total is 400. So there's my row total, times the column total for the column that cell is in is 470. And then the grand total is 800. So again, that's row total times column total divided by grand total. Now, I have a calculator here. We'll see what that gives us. Okay, 400 times 470 divided by 800. Okay, I got 235. So what I do, okay, you might not be able to read this because I'm going to have to write it kind of small, but I'd write a 235 up there. 2, 3, 5, kind of in the upper right-hand corner of that cell. So each cell now, each cell already has an observed cell count in it. If you want to pause the video and take the time to get the rest of the expected cell counts, I did the first one for you. Like this next one, to get the expected cell count for this next cell, the one with the 100 in it, you know, the row total is still 400. This time the column total is 220. So I take 400 times 220, then divide that by 800, the grand total, to get the expected cell count up there. Okay. Now, I'm going to leave it up to you to get the rest of the expected cell counts. But spoiler alert, I'm going to kind of show you a shortcut here a little bit too. Let me erase this. We've written our hypothesis statements. The next thing we would do is we would name the testing procedure that we're going to use. It's going to be the chi-square test for homogeneity. Okay. And then we're going to check the conditions. Okay. Here are the conditions. The conditions needed in order to run the chi-squared test for homogeneity. Okay, 1. Separate random samples from each population of interest. Okay, separate random samples from each population of interest. In other words, I can't take one giant sample of 800 people and then just put all the young people in this top category and put all the old people in that next category. To run this test, I have to take a sample from young people, okay, from among the population of young people, and then a totally separate sample, okay, a totally separate procedure to find a sample of from the population of old people. Okay. All right, and then the other one, okay, this is going to be the same as one of the conditions for the chi-squared goodness of fit test. Okay, all expected cell counts are greater than or equal to 5. Teddy, can you read that, boy?
Most of it. There's some, yeah, you can basically read all of it.
Okay, good to hear. Separate random samples from each population of interest. All expected cell counts have to be greater than or equal to 5. That's what it says. How are we doing time-wise, boy?
17 minutes.
All right, we're doing fine. Okay, so I've checked my conditions. Now it is time to calculate the value of the chi-squared test statistic. Okay, this is a chi-squared test. We're going to use exactly the same test statistic, chi-squared, that we did for the chi-squared goodness of fit test. So a reminder, the calculation formula for chi-squared is the sum of the observed minus the expected quantity squared divided by the expected. And I have to do that for every cell. Okay, so I'm going to have 1, 2, 3, 4, 5, 6 separate cells here. For each one of them, I have to take the observed cell count minus the expected cell count, square that, and then divide by the expected cell count. Okay. Then remember, this means add those up. So I do that for each cell, and I add up those terms, and that gives me chi-squared, the value of chi-squared. Now, something we need to talk about here, degrees of freedom. Okay, remember with the chi-squared goodness of fit test, the degrees of freedom was just the number of categories minus 1. It's different here. So let's write out, I mean, it's still simple, but the degrees of freedom, because remember, this is going to tell you which chi-squared distribution to use. So what you do is you take the number of rows minus 1 and then times the columns, number of columns minus 1. Okay, so we have 2 rows. Rows minus 1 then, 2 minus 1 is 1. Columns minus 1, I have 1, 2, 3 columns. So 3 minus 1 is 2. So this is going to be a chi-squared test with 2 degrees of freedom. Okay, the number of degrees of freedom here is 2. It's always this dimension minus 1 times this dimension minus 1. Okay. Erase that now. Okay, the moment you've all been waiting for. How do I do it on my calculator? Well, the calculator can save you some time when running a chi-squared test for homogeneity. Okay. If you've never used the matrix functions on your calculator, though, you're going to have to pay attention here. Okay, so pause the video, go get one of these, turn the calculator on. Okay. Now, matrix, the word matrix is right above the x to the -1 key, kind of on, it's on the left side of your keyboard. It's right there. So what I'm going to do is I'm going to go into matrix. Now, okay, I'm on the screen. I hit second and then the x to the -1 key. So I'm on the matrix screen now. Okay, what you have to do is go over to edit. Okay, so don't go down just yet. Just scroll right until the edit. It says names, then math, then edit at the top of the screen. Scroll over to you're on edit, and then let's edit matrix A. Okay, so in matrix A, what I'm going to do is, well, the first thing I need to do is I need to set up and see if my dimensions are correct, because I'm going to enter the observed cell counts into matrix A. Okay, so let's see. I have it's rows by columns, so this is going to be, we want a 2 by 3 matrix. So if you type in 2 by 3, it should build a matrix that has these dimensions for you. Then you can use the down arrow to get into the cells, and so I'm going to put a 250 in the top left, then a 220 in the one below that, then let's see, 100 top middle, 120. And then 50 and 60. Okay, so I did that. I filled in the matrix with the observed cell counts. Okay, now I'm going to exit out of the matrix page. I'm going to hit second and then mode to quit out and go back to the home screen. Now I'm going to run the chi-square test. Okay, notice I didn't say anything about putting any expected values or expected cell counts rather in a matrix, okay, because something magical is about to transpire. Hit stat and go over to tests, and then you'll have to scroll down. Now this is just called the chi-squared test. It's right above where the chi-square goodness of fit test. So I'm going to choose that. Okay. Now it says observed matrix. If you used matrix A like I did, just make sure matrix A is there. The expected, well, we didn't put our expected cell counts anywhere. Okay. Hopefully that'll be okay. All right. Mine says B right now, and that's fine. So I'm going to go down then to calculate. Okay. And when I did that, I got the following result. Chi-squared, value of chi-squared is 4.64. And the p-value then is 0.098. Okay. Well, p-values have really had the same meaning throughout the year. Okay, that's the probability of getting a sample like ours if the null hypothesis is true. A sample like ours, or more extreme if the null hypothesis is true. So that's about 10%, about a 10% chance of getting samples that work out this way, or more extreme if the null hypothesis is true. So about 1 out of 10 times you're going to get a sample that has characteristics like these, or characteristics where the TV viewing preferences are farther apart between the two age groups. Okay, so we all know that no matter what you choose for alpha, I mean 0.01 or 0.05, you're not going to reject the null hypothesis. So I'll write that. So I'm going to say since p is greater than alpha, and I know I never formally wrote down an alpha value, we'll just say it's 0.05. We fail to reject H naught at the 0.05 level. Now, I don't have room down there to, and you probably wouldn't be able to read it anyway, to write the second sentence in the conclusion. Okay, so I'm just going to say it. Okay, there is not sufficient evidence to conclude that the television preferences are different between the young category and the old people category. Okay, they may be different, the viewing preferences, but our sample didn't find sufficient evidence to conclude that. Okay, now One thing I wanted to tell you about the expected cell counts. Well, I only have one of them in here, and I never typed them anywhere. But like I said, something happened while we were doing that test. So let's go into the matrix function again. So I'm going to hit second and then the x to the -1 key. And we're going to go over to edit once again. This time, let's go into matrix B and see what's going on. Okay. Look at matrix B. Okay. The expected cell count in that top left cell was 235. Look what's in matrix B, 235. Okay. So what the calculator does when it runs the test is it goes ahead and computes, it does the row total times column total divided by grand total for each cell. So if you don't want to do those by hand, if you run the test on the calculator, it will populate the B matrix with the values for the expected cell counts. Okay, now, fair warning, if you begin this assignment without watching the next video, you may end up getting some of the problems wrong, because some of the problems in the assignment, of course, are going to deal with the other test, okay, the chi-square test for independence. That's going to be in the second video, so you might watch both videos before you try to begin the assignment. Okay, thanks for watching. Have a great day.